Good day everyone. So here's my report about nanoparticles in aqueous solution. Colloidal nanoparticles in aqueous solution have recently gained much attention for their potential applications. Particle agglomeration may either be required to occur in a controllable manner or needed to be avoided, depending on particular applications according to Yu et al. 2008. Particles with zero charge induced aggregation. Large particles can be obtained by combining them and they settle by gravitational force. In this figure, it is energetically and kinetically favorable for uncharged nanoparticles to collide and coalescence. It represents that nanoparticles with zero charge in liquid phase, in which it is easy for them to collide and form larger clusters. Particles are carrying electrical charges. A force of mutual electrostatic repulsion between adjacent particles is produced. That is according to Yu et al. 2008. In this figure, double layers of ions can protect colloid particles against rapid aggregation. They can be kinetically stable in an aqueous medium with identical surface charge. Encapsulation of the particles by silica in a 7.4 pH buffer is a way to produce stable and homogeneous nanoparticles. These particles do not aggregate due to the lower isoelectric point of the silica, rendering the overall particle charge negative. Particles possessing high charges can induce double layers in aqueous environments and are discrete, dispersed, and in suspension. This figure shows that a colloidal particle protected by a double layer of ions in an aqueous medium. In contrast with the repulsive energy, there is van der Waals attraction. The net interaction energy is derived from the resulting combination of repulsive and attractive energy. So let's now proceed to polymer nanoparticles for semiconductors. But first, let us define what is polymeric nanoparticles. Polymeric nanoparticles are particles within the size range from 1 to 1000 nanometer and can be loaded with active compounds and dropped within or surface adsorbed onto the polymeric one. The term nanoparticle stands for both nanocapsules and nanospheres, which are distinguished by their morphological structure. Polymer matrices are embedded with metal in order to provide materials that possess unique properties arising from the nanoscopic size or shapes of metal clusters. Polymer nanoparticle composites are prepared by in situ generation of metal nanoclusters and assembly of polymer scaffolds with monolayer protected clusters to prevent agglomeration and provide good handling and processing options. Self-assembly of nanoparticles with polymers is providing access in order to stabilize metal and semiconductor nanocomposites for the fabrication of new materials. However, many attributes of the individual building blocks like size and shape of individual metal clusters, composition of the monolayer, and the functional groups on polymers would allow controlling the properties of these nanocomposites. So the following figures are the proposed mechanism of the functional nanocomposite hydrogels under the sunlight. Figure A is the semiconductor nanoparticles, monomer, and clay nanostructures are homogeneously dispersed in water. And B, when exposed to sunlight, polymerization is initiated by the semiconductor nanoparticles. And next is letter C. The nanoparticles and clay nanostructures are cross-linked to develop a 3D network. Letter D, optical images of the hydrogelation process. A mixture solution of zinc oxide nanoparticles, dimethylamine, and clay nanostructures. Letter E, hydrogelation after 1 hour of irradiation. The next is letter F, the elastic zinc oxide nanocomposite hydrogel. Letter G, scanning electron microscope image of the zinc oxide nanocomposite hydrogel after supercritical drying. And the last is the transmission electron microscopy image of the zinc oxide nanocomposite hydrogel after a biocutting treatment. That's all my report for nanoparticles in aqueous solution and polymer nanoparticles for semiconductors.